Okay. First of all, let's recall how to find, well, let's talk about a horizontal asymptote. Okay? A horizontal asymptote is where your function approaches as you reach infinity or negative infinity. Okay? What we are going to talk about today is limits evaluated at infinity. Okay? Yesterday we evaluated limits that equaled infinity. Today we're going to evaluate limits as x goes to infinity or as x goes to negative infinity. Basically, we're talking about the behavior of the graph. Okay? So here I have a graph with my horizontal asymptote. Okay? So what we say, our horizontal asymptote is here at y equals 3. So if I were to evaluate the limit as x approaches negative infinity of this function, as we go to the left, forever and ever, our graph is approaching that horizontal asymptote of 3. Okay? The limit as x approaches infinity, our graph increases with a bound, right? Okay? We approach that horizontal asymptote of 3. Okay? Basically, a limit at infinity is explaining the behavior of the graph. Either we're going to approach an asymptote, or we're going to increase or decrease without bound. Okay? So here we go. Limits at infinity are going to describe the end behavior of a function. Okay? More specifically, we're either going to look at if it's increasing or decreasing without bound, or is there a horizontal asymptote that it's approaching. Okay? If there's a horizontal asymptote, we know that as we go out towards the infinity, that is what our graph is approaching. Now, before we get into our rational functions and figuring out where asymptotes are and yada yada yada, I want to talk about polynomials. We know how to determine the beginning and ending behavior of polynomials, correct? What's that test called? What is a test? Mm-hmm. It's called the leading coefficient test. Oh. Right? Yeah. If we have a positive leading coefficient, what does that mean about the right side of our graph? Okay, so the right rises, correct? If we have a negative leading coefficient, what does it mean about the right side? Okay, it's going to fall. Okay, I'm going to use very informal terms, if that's okay. So that's how we think of it anyway, right? Falling or rising. Now, what if we have an even degree? What's true about the left and right sides? They're the same. If we have an odd degree, what's true about the right and left sides? Left, right. Left, right.
You don't have to.
I will. For you. Okay? So if you are given a limit at infinity for a polynomial function, you need to think about what the beginning or ending behavior is so you can describe your limit. Okay? Obviously, polynomials increase or decrease without bound, so technically the limit does not exist, but we can describe it as either infinity or negative infinity. Okay? It's okay to do that now. All right? So, here we go. The limit as x approaches infinity of 2x to the fifth, and then we have the limit as x approaches negative infinity of 2x to the fifth. So let's talk about 2x to the fifth. When we are evaluating the limit as x approaches positive infinity, we're talking about the right side of the graph. So what's happening on the right side of the graph? Are we rising or falling? Rising. Rising, because we have a positive leading coefficient. Now, I want the limit as x approaches negative infinity. That's talking about what is happening on the left side of the graph. We have an odd degree, so what's happening? It's falling towards negative infinity. Okay. What about 5x to the sixth? Okay. What happens towards positive infinity? Towards negative infinity? Our next function, negative 7x to the fourth. What is happening on the right side of the graph? It's falling because we have that negative leading coefficient. What about the left side of the graph? Also falling because we have an even degree. Okay? Really, we have not talked about anything new, right? We know the ending behaviors of their polynomials. We're just describing them with a limit now. Okay? I would like you to look at this one. Devin, what's our limit? Positive? You agree? Okay, we have a positive leading coefficient, so we are going to rise on the right side. Look and think about this one. Aaron, you seem fancy to answer this one. Oh, I thought that was a. Oh, I want to answer.
Okay, now I'm ready.
Okay, what is it?
Negative.
Why?
Because it's an odd exponent and it's
Which one is your leading coefficient? Which one's your leading coefficient?
didn't
Just tell
even
me.
realize that. Don't do that.
You answered it with the right
I still would have gotten the right
description.
answer.
Okay, so I didn't trick you enough. We have an even degree and a negative leading coefficient. Make sure you put the polynomial in order before evaluating the limit. How many of you got tricked? It's okay if you did. That's why I put it up there. Okay? Look at the highest degree. That is your degree and leading coefficient. Okay? All right. Moving on. If you have a positive rational number, okay, c over x to the power. If I look at the limit towards infinity or negative infinity, it is 0. Why?
there only being an x variable on the bottom causes a horizontal asymptote at 0.
Okay, that's good. What's another explanation? What's another way you can
When
think
the
of it?
degree in the denominator is higher than the degree in the numerator, then the asymptote is always equal.
That's the same explanation. Is there a different explanation that you can think of?
Oh, I thought it was times.
As x increases to infinity, the fraction gets bigger.
Okay, as our denominator gets bigger, our fraction approaches 0, right? If you want to think of that numerically, you just gave an example of an asymptote, right? So, if you have the limit, you know, as x approaches infinity or negative infinity of 1 over x, 1 over x squared, 1 over x to the 15th. No matter what it is, if you have a constant over x to a power, the limit towards the infinities are going to be 0. Okay? The magnet fell off. Okay. So we're going to do this example. Can you see it? It seems awfully small. Okay. Okay, so what we can do is we can break this up, okay? We're subtracting two functions. So remember, this is the same as taking the limit as x approaches infinity of 5 minus the limit as x approaches infinity of 2 over x squared. What's the limit as x approaches infinity of 5? 5. Minus, what's the limit as x approaches infinity of 2 over x squared?
0.
0. So this is 5. What?
I didn't even know you could do that.
Do what?
Well, like, I knew that you could take the limit of them separately, but, like, I never thought you could think of them, like, I never had the idea of thinking of them as separate functions.
As separate, yeah. You can think of them as separate limits, or you can evaluate them separately and subtract, okay? You wouldn't have to write this out like this if you didn't want to, okay?
Somebody
Yeah.
could just write the function. Maybe requiring shit like that.
What I would prefer, like, if you say that, okay, I know this goes to 0, so I have 5 minus 0, which is 5.
That's fine.
That would be fine. Okay? So whichever you prefer, however you want to think about it. Okay? Okay. Now we're going to get into some more hefty rational functions. Like this one. Okay? Now, I know you all are thinking horizontal asymptotes, right? Before we think about horizontal asymptotes, I am going to give you a rule that can be applied to any rational function. We are going to see rational functions with roots later on, okay? So I want to give you a rule that you can use no matter what kind of rational function you have, all right? So, first of all, okay, this is something that, Aaron, you asked yesterday. If I evaluate these limits separately, we would have infinity over infinity, okay? That is not okay. That is what we call an indeterminate form, okay? Because it's not 1, okay? So what we can do is we're going to look at the highest degree in the denominator, and we're going to divide each of our terms by that x to a power, okay? X to whatever power it is, okay? So in this case, what is our highest degree in the denominator? 1. So what we're going to do is we're going to divide everything by x. Okay. what happens? Okay, we have 2 minus 1 over x over 1 plus 1 over x. And what happens with the limit as we go towards infinity of these 1 over x's? They become 0. And we're left with 2 over 1. Okay? Now, if I give you a function like this, that is not necessarily the method that is the quickest. Right? What is the quickest method?
Looking at the degrees, they're the same, it's just the ratio.
Okay, in general, we're looking at the, what are you finding when you are doing that?
Ratio.
Horizontal asymptote.
Okay, we're looking at where the horizontal asymptote is. Okay? If you have a rational function, we know there's going to be a horizontal asymptote, and that is what our graph is going to approach. So, let's recall our horizontal asymptote rules.
I like the little arrow. I'm gonna start using the little arrows.
Okay, yes.
If you know, okay, so we divided by x. If there was a coefficient on the bottom, would we divide all of them by the coefficient as well?
No.
It would just be x.
Just the x to the power. Okay, so if the degree of the denominator is greater than the degree of the numerator, where is our asymptote?
0.
Please, you want to say specific?
Y equals 0.
Why did you be specific? Okay. If the degree of the denominator equals the degree of the numerator,
Y equals the ratio.
okay, we look at the ratio of the leading coefficients. And what about if the degree of the denominator is less than the degree of the numerator? What is happening? Okay, we have a slant asymptote, and so we would have some unbounded behavior. We would either be going to infinity or negative infinity, and we would have to make that decision. Okay? And I'll show you how to do that. Okay? So you ready? Here I have the limit as x approaches infinity of 3x plus 5 over 6x minus 5. We are worried about the behavior on the right side of my graph. This is a rational function. We have a horizontal asymptote. Where is our horizontal asymptote?
Y equals 1.
Okay, we have a horizontal asymptote at y equals 1/2. That is what our graph is going to be approaching. So that is the limit towards infinity. Okay. Okay. What's happening? We have a slant asymptote. So we need to decide whether we are going towards positive or negative infinity. All right? So we're going to have to fall back on our method that I told you about before we talked about asymptotes. Okay? So what's our highest degree in the denominator? X to the first, correct? So we are going to divide everything by x to the first. So what are we left with? We're left with 2x minus 4 over x over 1 plus 5 over x. Okay? Well, we know that this 4 over x goes to 0 and this 5 over x goes to 0. And we're basically left with, but the limit as x approaches negative infinity of 2x. 2x is a what?
Line.
A line. Negative infinity, that's the left side.
Negative infinities.
Okay? It's falling towards the left. So this is negative infinity.
Is that the line, like, of the asymptote?
No. The line is when we actually do the division.
Oh, right.
Mm-hmm. Like the long division.
Yeah.
Yeah.
Do you have to do that?
Which I guess
Be 2x.
it would be 2x.
Yeah.
So this was a special case, but that's not always going to happen. Okay. Okay? Here we go. Please do not be fooled by this one. Okay. First of all, I have a rational function. We're going toward, it doesn't really matter if we're going towards positive or negative infinity with these because we're approaching the same asymptote. Degree in the numerator, degree in the denominator. Where's our horizontal asymptote? So our limit, we're approaching that horizontal asymptote. Okay. Aren't you so thankful that you studied rational functions and polynomials so much that you can answer these questions without much thought? It's a good thing we took pre-calculus, isn't it? It's a very good thing. Okay. Write it down. Okay. So here we have to be careful. Okay? You cannot strictly look at where our asymptote is. Okay? A lot of us want to say right now what? Okay. Technically, we have the same degree upstairs and downstairs, don't we? Okay. That square root is going to kind of throw a wrench into things. Why? Okay. Okay. When we have a square root, we are very limited, aren't we? We're limited on what can be under there. Okay? So, we need to be careful. When we have a square root in the denominator, really any even root in the denominator, it's going to create two different asymptotes. And so we need to figure out which one that we're approaching. Okay? So, this is when we need to fall back again on that method I told you about before. Okay? So, technically, what is the highest power in the denominator? It is not x squared. It is x to the first power. Why?
1/2 times 2.
Okay, because it's the square root of x squared. So x to the first is our highest degree. Okay, now when we have the square root of x, as long as x is positive, okay, x is the same thing as the square root of x squared. Do you agree?
Yes.
Why did I say when x is positive?
Oh,
Okay, but why in this problem did I say when x is positive? Why did I pick that to talk about? We're going towards the positive side of our graph, right? So I'm only worried about when x is positive. Obviously, this is gonna change if x is negative, isn't it? Okay? So, we're gonna go ahead, we're gonna divide by that x to the first power. Under our square root, we would be dividing by what? Okay, if we're in our square root, we need to divide by the x squared, because the square root of x squared is x, right? Okay. So what happens? We have 3 minus 2 over x over the square root of 2 plus 1 over x squared. Here I have a constant over x, it goes to 0. Here I have a constant over x squared, it goes to 0. And we are left with 3 over radical 2.
Or do you want us to change it into 3 radical 2 or 3 or just leave it?
You know what? The AP test does not care if you simplify. You can leave it like this.
Right.
Welcome to AP Calculus.
I like that.
No, it is not a lie.
Maybe it's especially no.
You know that this is 3 radical 2 over 2, but the AP test is not going to force you to simplify. Now, if this was a multiple choice question, they probably would have 3 radical 2 over 2. Okay? If it was a free response, you would not be deducted points if you left it like that. That's the difference. Okay? Now, I want to look at as we go to negative infinity. Okay? Now, x to the first, that's our highest power still, right? However, when x is negative, what's true about x compared to square root of x squared? And so we would need to write that, correct? If x is negative, I would have to negate my square root of x squared. Because that square root of x squared is always going to be positive, no matter what. Okay? So how is this going to affect our limit? Okay? We're still dividing by that highest power, right? But the square root of x squared, okay, needs to be negative because we're going towards the left side. So what is this limit going to be? Okay. So it is not as simple as looking at the leading coefficients when there's an even root downstairs. You need to go through what it means to be on the right side, what it means to be on the left side, because we have 2 different asymptotes. You're going to have to pick one. Okay. These are going to be the hardest problems on your assignment, probably. Okay? Will be. I think. I don't know. You might think something else is harder. You might think that's easy and something else is hard. So I'm not going to say.
That makes
Okay. Here's your homework.